So one of the important things to think about with random variables, one feature that they have, and something that's really useful and important for us to know, is that a random variable has an expected value. So when there's a random variable that we are able to assign probabilities, likelihoods to the different possible outcomes it can take, that means it's a random variable that has an expected value that we can calculate. An expected value is similar to an average. In fact, we often use the same Greek letter mu to designate expected value that we use for a population average that we talked about way back in the beginning of class. But expected value, you can think of it as a central tendency, as a likely, our best guess as to what is going to happen with a random variable. So let's think about a random variable of how long stay-at-home order is going to be in place because of the COVID-19 pandemic. We don't know how long that's going to happen, right? There's uncertainty there. Let's say we have a simplified version of reality, and the stay-at-home order could either last 20 days or it could last 80 days. So those are the two possible outcomes. So in our simplified world, we know that the stay-at-home order is not being lifted in the next 19 days. We also know it's not going to last more than 80 days. We also know it's not going to be some intermediate amount. We know it's either 20 days or 80 days. So obviously that's a gross simplification of the real world, but it'll help us think about an expected value. So if the stay-at-home order is, if we think it's equally likely to be lifted in 20 days or in 80 days, so there's a 50% chance, a probability of 0.5 that it gets lifted in 20 days and a probability of 0.5 that it gets lifted in 80 days. What is the expected value of this random variable of how long we will have stay-at-home orders in place? Well, we're going to take the different outcomes and multiply them by the probability that they're going to happen. So one possible outcome is 20 days. We're going to multiply that by the probability of 0.5. We're then going to add that to another possible outcome, 80 days, multiplied by the probability that happens, 0.5. So if we do that, we type in 20 times 0.5 plus 80 times 0.5 into a calculator, hit the equal sign. It's going to tell us the expected value of our stay-at-home order is 50 days. That makes sense, right? It's in between 20 and 80. We're weighting those two things equal. They have the same probability. So our best guess as to how long this is going to last is 50 days, something right in the middle. Now notice in our simplified version, there's no way that we can actually have a stay-at-home order for 50 days. It's either 20 or it's 80. The expected value is kind of showing us what's in the middle. It may not even be a possible outcome, but it's in the middle. It's our best guess as to what to expect, even if we don't expect that particular value to happen. Now, let's say we're more optimistic that the stay-at-home order is going to be lifted sooner rather than later. Let's say we put a 75% chance on it being lifted in 20 days, and that leaves just a 25% chance that it gets lifted in 80 days. So we can do that math. We can type 20 times 0.75 probability plus 80 times 0.25 into a calculator, and that's going to give us 35. So now our expected value of the stay-at-home order length is going to be 35 instead of 50. Why? Well, because we're weighting the lower outcome more. We put a probability of 0.75 on 20 days. That's going to pull the expected value for this variable down lower, closer to that value that we're weighting more. So the expected value is a weighted average. It's telling us kind of what our best guess as to what will happen, and we see it get pulled by things that are more likely to happen, such as, in this case, a lower value for the number of days we expect a stay-at-home order to be in place. So we can calculate an expected value whenever we know, when we're able to assign probabilities to different outcomes. those may be subjective probabilities. They may be ones that we're kind of guessing, we're using our gut, maybe they're informed, educated guesses. Maybe we have, a model telling us how likely different things are to happen. However we get the probabilities, if we can put probabilities to all the potential outcomes, we can come up with a expected value by taking each value this variable can take, multiplying it by the probability of that happening, and adding all of those things up. So we're going to sum all of the potential outcomes multiplied by the probability of that outcome occurring. In our example, there were just 2 possible outcomes. We could have added a third, a fourth. We could even add an infinite number of possible outcomes. When we have that, it's a continuous variable. So we talked about that a bit back before. If something can take any value on the number line, then it's continuous. We're not going to work with those in this class because we would have to use integrals. So we're going to use examples of discrete random variables where it can take particular values, 20 days, 21 days, 22 days, 23 days. We can assign probabilities to each of those, right? We're not going to have stuff where we're working with 21.04789, blah, 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 blah. And for practical purposes, we're going to use random variables with a limited set of outcomes. So not only discrete, but a fairly small number of possible outcomes. Otherwise, it just takes a really long time to sum up all of the possible outcomes multiplied by the probability that they'll happen. So you'll see a lot of examples of 2, 3, maybe 4 potential outcomes, and I ask you to come up with an expected value for that. And we'll do it by taking the possible outcome, $80 times the probability that it happens. It happens with a probability of 0.1. Okay. Then we add that to the next possible outcome, $0. That happens 80% of the time, multiplied by 0.8. Add up all of the different possible things. Hopefully your probabilities should all add up to 1, right? Because we're looking at all the possible outcomes. That means when we add all of those probabilities together, we should have 100% represented. We should have them add up to 1. So that's how you calculate an expected value. And that is something that we'll be doing on homework and we'll be doing on the next quiz coming up.